Back. This is a second program looking at the TF runs package from RStudio. And what I've done is in the prior video I talked a little bit about how I was going to expand the program. I'll walk you through a little bit of what I've done here. I will post the actual code on my website and the link will be available with the video. But basically one of the problems with training a convolutional neural network is the sheer number of parameters and configurations you can consider. I've set this program up to have what is, I hope, a relatively flexible structure. When I've tried it on my BPU data, one of the things that stood out was that the performance wasn't quite what I wanted. So I wanted to step back and see if it was the program or see if it was related to just a challenging data set. So I'm going to look at the MNIST data here. Obviously not the most exciting data set, but something that I know can have good performing models created. So as you scroll through here, one of the things you'll see is there's a lot of flexibility. I have only 2 activations, but you could easily expand it. I have a couple variables that determines how many convolutional cycles I want, how many dense layers at the end, what sizes of the nodes. You can give each of the parameters a default value and some description. The model goes through and it's a little cumbersome because what I'm doing is rather redundant coding, but it's to make it flexible so you can see if I'm checking some activation functions and then specifying the individual layers that would be applicable, and obviously this can be expanded more if desired. So when we switch over here to the data, you can see it's standard MNIST. I'm not going to go into much detail there. It's readily available elsewhere. The basic structure is I'm going to call a tuning run and put those data into this object called runs. This runs object will be able to store all the results, and we'll be able to go back and analyze that. And I'll look at that after this completes. Right now, it looks like you can only sample a percentage of your randomly generated tuning configurations. It'd be nice if I could just specify, sample the top 100 or something like that, but it doesn't appear to be the case. I have 12 gigs of GPU RAM, so I'm going to try to put in 256 on the batch size to see if that'll speed things up. I'll go ahead and change the number of epochs to be 20. That's a lot of what I've seen with MNIST is around 15 or so. I'm not tuning the default rate. I'm just going to pass it through here. I don't know. Times I've tried to change it from, say, Atom. Atom is the optimization algorithm used here. It doesn't always work as well as I'd like. In this data, I have a image augmentation configured into the program skeleton. So I'm going to let it see if image augmentation helps the training. I'd expect the internal validation to look a little bit lower, but we will see. Flip is one of the things I'm interested in. Is when I set up the image augmentation, I just kind of picked all the options. One of the options was this horizontal flip. On a digit recognition problem, I would think a horizontal flip could be detrimental to performance. So in this case, I'm going to look in and be able to test that maybe more systematically, and by testing both the true and the false in the image flip. If image augmentation is false, I'll do a validation split, so I'll get some measure. Otherwise, if it's augmenting, it's going to do the real-time image generation on the holdout data set. Number of convolution cycles, the dropout, a couple different activation functions. Here I'm going to look at whether or not mean or max pooling gives better results. I've seen some discussion that it depends on the data at hand. For the BPU data I've been looking at, it seemed like mean pooling was working better. Curious what it'll do on the MNIST data. Padding is 2. I could set up some different pooling size. Since the MNIST data is relatively small, I'm going to keep it just at 2. Filters, I'm going to look and see from 32 to 96. Number of dense layers is number of, I basically have 2 structures for the fully connected layers at the end. I'm going to look at one set of type 1 and then another set of type 2. Each of those say, components of the layers can have a different number of hidden nodes. Dropout I have at 0.5. Obviously, I could have tuned that as well. So I think this might be about 100 runs to do. It may take a little better part of the day, but I'm just going to let it run off in the background. A nice thing it will give you is it says 207 combinations. I think that's about 5 hours worth of computing, so that'll give me enough data to play with in say a post hoc analysis. So I'll go ahead and say yes, and I'll let you watch the first one as it gets triggered. So it conditionally writes all the model statements. It's feeding it to the GPU. My data was already preloaded, so I don't have to go back and re-download or load that into working memory. So this, if you're curious of what the pass is, you can scroll up, you can see the architecture. Definitely a deep model here that came out. You can see what the tuning is. So this is a little clunky, but it's 256 batch is what I was expecting. We're going to do real-time image augmentation, so this one will run slower. Flip in this case is set to true, so it's going to do image flipping. What else is potentially interesting? Just some of the other complexities. So the hidden nodes are going to be relatively small. So my guess is the performance here may not look great, but we will see. And you can probably hear the GPU starting to spin up as it's being fully taxed now. Models converging, and now we wait. It'll cycle through. 11 seconds per epoch's not too bad. May not be too many hours before it's done, but we'll wait and see. All right, I'll check back in a little bit. Bye-bye. All right, we're back. The GPU ran for about 7 or 8 hours today. Finished up for the day, so I'm going to just take some of it home. Ended up stopping early. Couldn't finish all the 200 runs. We can do a couple quick inspections here just to see what we ended up with, and I'll try to do a little more formal analysis with time. So you can see maybe this last one didn't quite finish. We have a total of 87 runs. We can sort a little bit by accuracy to see what we're looking at. Some quite poor performing, 65%. We have a lot, high 90s, high 9.2, so it should be fun. We'll look at it shortly. We're back. We're going to look at some of the results of the training runs. Get started, I'm going to load a couple of the packages on the data object here. Finished runs is the results of the TF runs package. I saved that at the bottom. I wrote a quick helper function here to do a series of GG plots. I'm going to take the data frame, finished runs, pull off the names, and then filter off the variables that start with the word flag. And that's actually something nice that TF runs does. It gives you a data object that you can easily manipulate. And then I'm going to go ahead and generate the series of plots. This will just take a second. And while that's running, I'm going to flip programs, and we're going to go from the bottom up as we look at the results here. So drop 2 is the dropout for the dense layer. I didn't really actually have it set in anything. It's 0.5, and so this is just random noise going back and forth. We tried a couple of different parameters looking at the number of hidden nodes within the dense layers at the bottom. As I'd expect, just based on the number of convolutions, more density down low seems to give better results, more uniform results. The next one, so if you recall, as we set up the generic architecture, we had 2 chunks for the dense layers at the bottom. We could set the number of nodes separately for each. Again, similar pattern. You'll see this reoccurring set of about 6 observations that seems to perform poorly. I looked at, part of what I'm seeing is they were incomplete runs. Maybe they were some where I was starting and stopping the training, or they could have just failed. We can look at those separately as we want. Interestingly, for the validation for the dense layers, the leaky ReLU seems to work better, and I was maybe a little expecting ReLU to do comparably. Again, the model's performing exceedingly well, but much more consistency with leaky ReLU. Moving up, we go through this, the number of dents 2. This is the number of dense layers, how many times, or how many different layers of the dense architecture do we have. These are a little bit noise. It looks pretty balanced. I think the model was training and converging relatively quickly. This is also similar. This is the dense layers of type 1. Backing back a little bit, the filter 3, that's the size, that's the number of filters for the third convolution within the set. More filters, as we're going to see, seems to be the key for this data, so potentially estimating as many filters as you have GPU RAM may be a good strategy. We can go through these. We'll go a little faster now. You can see there's not a lot of discrimination. Kernel 2, I don't actually think I set it anything, so this is just the jitter spread on the data. Same thing for that. Looking here, moving through, a lot of consistency. We only considered one padding. Mean pool, this was a question of whether or not we want to do mean or max pooling. So if it's true, we did mean pooling, and if it was false, we did max pooling. Pretty comparable results. I was surprised with that. This is the activation for convolution. Here, I think the ReLU is the better choice. This is what most people frequently use. When I did the leaky ReLU, which if you're not familiar with that, it allows, instead of it being 0 all the way up to this thresholding point, it allows a very small slope up until that, and so potentially is less of a strong penalty on the activation function. We can go back a little bit more, looking at dropouts. These were set at 0.5 universally, so it doesn't really change much. Number of convolutions. This is, if we look over here on our list, we're moving up the number of extra convolution cycles. I don't remember how many we allowed that to vary, but we can see here. So that was just set at 2. We could have trained more on that. Validation split. So this, again, only applies if you're looking at non-augmented data. If you're doing data augmentation, it doesn't do the internal validation split. Flip is a part of the image augmentation, so whether or not you take the mirror image, I was a little surprised that this came out. I mean, so you do see potentially a little bit of a shift where having some type of flip decreases the overall accuracy. This would make sense, although I guess you could represent or train models to look at the sort of the dyslexic view of the numbers. But given we're trying to match numbers, it seems like flipping could be detrimental to the training, but didn't seem to be. Whether or not you add image augmentation. So adding image augmentation on the validation accuracy does seem to have lower accuracy. That makes sense. It's essentially making all the images harder and less likely to be overtrained to. So that was a relatively big finding. That's something I noticed on some of my breast imaging data I'm looking at. Introducing image augmentation does seem to introduce some challenges to the training. It's good challenges, but challenges nonetheless. So learning rate, I didn't set it anything. I more or less used the default value, and number of epochs, I did a straight 20. Looking at batch sizes, didn't see a lot of difference, again ignoring some of these really low values. it certainly does make it train faster if you can put more data into the GPU. So those are the results. We'll go back over here. We'll look at some of the next things. So here are those poor models. I can look at those, pull those out into a data object. You can see we can sort them maybe by the validation accuracy. Oh, now my R is broken. We're back. It's real life data modeling on the edge. All right, so we'll look at this. So our poor models object did come back. There's, you could probably go through here. The fact that some of this looks like it's missing seems to suggest that those are incomplete runs. We'll take it as that for now. So looking down here, one of the next things we want to do is possibly pull in the best model and see how well it performs. I can do that quickly by filtering and arranging based on the validation accuracy. I'm going to go ahead and pull off the tops sorted by validation accuracy, call it my best run. You can look at some of the objects you'd have access to. I'm going to go through and pull off this run directory so I can pull in the saved model. At this point in time, my GPU is not attached to the laptop, so it's going to run a little bit slower. So when it crashed, I didn't get my packages. Let me do this. So we'll do this now. This should run. It's going to load the model. And yet another crash. All right. Get good at that. We'll do this. This again. So this is a normal error without the GPU. The way that I have TensorFlow compiled, it does look for the GPU, and so when I try to load it, it'll report that. But this should still work. You'll notice how much longer it takes to do some of the training. I'll go through. This normally doesn't have to be done. But as you've seen, my computer's, or the RStudio's crashed a couple times. So we'll go ahead and run it. This last predict step is running the prediction on the test data. And what you'll notice is this took, essentially no time with the GPU. Without a GPU, it does chug. Gives you an idea of maybe how much benefit there is to using the GPU for deep learning. But it will run. It'll only take a few more seconds if we're lucky. And then I'll talk you through what we're going to do next. I'll just open up some of the top predictions. I'm going to do a simple table. I'm going to use the caret confusion matrix. It just has a nice format to the output. Certainly better than the raw table. But you can feed it in the table. And the order is important as well for all the sensitivity specificity that is calculated. You start with the predicted and then you row by column to your columns you want to put your truth up there. So our predictions are done. We can go through, we can see a little bit. So first object was 7, 2, etc. And then when we do our confusion matrix, we end up with a nice format. And this just shows how well convolutional neural network does for predicting the digits. There are a few that are misclassified, so we're predicting a 1 when in fact it was say a 7 or a 6. Seems like it's plausible, particularly as people may draw sevens without a pronounced top across it. But overall, it looks good. There's a 99.52 accuracy. And then one of the things I was going to do was just loop back through. So we did that. We see what that validation accuracy is. While these are poor models, you see the evaluation loss in accuracy. And if we were to go back to the full data object, let's see, finished runs, we sort it by validation accuracy. We pulled this off, and here's the, oops, sorry again. And there's a 99.52, which is again this estimate. So as we were running our models, you notice on our skeleton program, we have our architecture, and we concluded the program with the saving of the model as well as this evaluation step. And so it's pulling out and putting this into the data object. So it was nice. I showed you just how to use the predict just to give you an idea of the speed difference, but you can actually pull all of that out from here. And so in terms of some of the best evaluation accuracy, we were up there at 99.55 and 5.2, which are essentially neck to neck with negligible differences over here. So I have this code. I've posted it on my website. I'll post the link in the description below. And thanks for listening. Bye-bye.